What is the single most important responsibility your classes should have? Let's find out together in today's episode of Codesday. A class should only have one reason to change. This is the single responsibility principle, one of the 5 solid principles. Although the statement refers only to classes, I believe it applies to methods as well. Today, I would like us to look at some code that initially doesn't respect the single responsibility principle. We'll understand the reasons why, and we'll write tests in a test-driven approach, tests that will force us to refactor the code such that in the end, it will respect the single responsibility principle. Let's have a look. What I have here is a static method in a static class that computes some statistics about our users, namely the age average of the first 5 users in a database. The issue with this method is that it not only knows how to calculate the average, but also how to retrieve the data. It knows about the database and how to connect to it. It even uses anti-framework. So this clearly violates the single responsibility principle because there are at least 2 reasons for this class to change. The first reason is related to how and where the data is retrieved from. The data is currently stored in the database, but in the future we may want to retrieve it from a file system or an external service. Alternatively, the data will no longer be retrieved with Entity Framework, but rather with a different ORM. And the second reason has to do with what happens with the data once retrieved. Imagine that instead of computing a simple average, there would be another piece of business logic that would be much more sophisticated. Therefore, I intend to refactor this code using unit tests and a test-driven approach. What you want to do generally is write a test before you touch the code, a test to ensure that the current functionality is locked in place so that your original behavior is maintained throughout the refactoring. As an aside, the refactoring process and actions are designed to ensure that the behavior does not change, but just to be on the safe side. I've already written such a test, is this one over here, and it's hard-coded because it exercises the system under test as is right now. And the current situation is that our system under test, our method, knows how to connect to the database, it has all the connection string details, and it uses anti-framework to do so. And my current setup is that I'm having a Docker instance running on my local computer, hosting a Microsoft SQL Server instance. And inside this instance, I have a small sample database with mock data. This data happens to contain a list of users whose ages average to this value of 30. So now, just to prove that the system works as is before we even do anything to it, let's try and run the test and see if it passes. And it does. Because I intend to use a test-driven approach, I will begin by modifying the existing test, which will require us to change the source code. This will be the driving force throughout the development process. The goal is to extract the existing user reading functionality in a dependency in order to relieve the method of this responsibility. The benefit of this is once created, it will be possible to mock this dependency and put the test in charge of the test data. As a side note, designing tests that interact with the database is perfectly acceptable, but those tests are not unit tests. So first and foremost, I want to change the existing test to prepare the now static class to accept dependencies. These dependencies will be managed both at runtime as well as test time. I will start by writing the code I would like to have. Don't worry if the code does no longer compile. In test-driven development, there must be a failing test first, and not compiling is failing. And then the code must be altered just enough to pass the test. So let me modify the test. So what we would like to have is have a variable into which we assign a new instance of our user statistics class. Obviously, this does not compile yet because the user statistics class is static. So all we have to do to make the test pass is to go in the code and remove the static modifiers. Once we've done that and the code compiles again, we should be able to run our unit test and it should pass. And it does. Now that the class can accept dependencies, let's construct and inject a dependency. And I know I've said we modify the tests first, but I want to make use of Rider's refactoring capabilities to ensure that I'm only performing refactoring operations. So what I want to do is select this bit of code in here, and we'll first extract it into a method. A method called first5users, and we're going to make it public and non-static, and I'll explain in a second why. The reason is we want to export this method in a class of its own, because otherwise our user statistics class is going to violate the single responsibility principle itself, and we don't want that. So I'm going to refactor this to extract a class which we'll name user reader. Next. And Rider has extracted the class for us and moved our method in it. What we have now is a private field which is instantiated, is initialized on the spot, and we don't want that. We want to move this this new instance creation outside of our class to have it injected into the class as a dependency. And we're going to refactor this to introduce this as a parameter. And I'm going to call the parameter user reader. And Rider has already pushed the new instance creation outside of our class, so into the clients, namely the test. At this point, you would think that our method adheres now to the single responsibility principle. I mean, I removed one of the responsibilities from the method, so it should be fine. After all, it started with 2 responsibilities, I extracted 1, and now we're left with 2. Yes, in programming, 2 minus 1 can sometimes equal 2. Allow me to be more specific. Even though I moved data acquisition outside of the class, the method still has 2 responsibilities, specifically calling the user reader to obtain its data and then doing something very specific with that data. So there are still 2 reasons for it to change. Either the way it interacts with the user reader changes, or what happens to the data after it is required changes. Furthermore, as trivial as it may appear, calculating an average on a list of numbers can change in the future. Perhaps someone will devise a more efficient algorithm to compute it, or we may even use another library or something similar. As a result, extracting it in its own dependency makes sense. At the very least, the average calculation is such a basic feature that it might be used elsewhere in the code. As a side note, a method should always function at the same logical level, and contacting a dependency and performing a very specific task like computing an average are 2 entirely different logical levels. So let's do this now. All we have to do is select this bit of code and again extract a local method. We'll just call it average. Again, public and non-static. And now we want to extract a class which we'll name math calculator, and we want to inject this dependency. So we'll just introduce a parameter math calculator, and Rider has pushed it all the way into the client, namely our test. And I'll just clean this up a bit. We don't need the constructor in there. And if we run the test, it should still pass. And it does. So I've separated the 2 responsibilities that have been crammed into the single method into their own dependencies. Surely, now the class and the method respect the single responsibility principle. Not so fast. Currently, we test the method by injecting concrete dependencies, and the only way we can manage the test data is by modifying it in the database, which is often more difficult to do, and in this instance, completely unnecessary. Consider that the primary purpose of this test is to verify that when a collection of users is supplied, the correct value for the average is computed. So why should the database be involved in any of this? Couldn't we just provide a list of users from an in-memory store and call it a day? Sure we could. However, to do this, I must slightly change the relationship between the method and the user reader dependency. the dependency must be hidden behind an abstraction in order to replace the implementation at test time, an implementation that would allow injection of arbitrary lists of users. And the only true abstraction in .NET is the interface. So what we want to do is come up here into the user reader class and perform another refactoring, which is extract interface. And we're going to call this iUserReader and just hit next. And Rider has created for us an interface, and now our user reader dependency implements this interface. All we have to do is come down here into our original method, or original class, should I say, and perform use base type where possible. And the base type we want to use is the actual interface. So if I hit next, Rider changes all the references that were until now directly to the user reader class. Now they point to the interface. So our tests should still pass, or should I say our test. So let's try this now. And it does. Great. So I successfully extracted an interface for the dependency and used it in code. This would allow me to write tests in which, given another implementation that meets the new and shiny contract, I could control the data coming into the method and test with various lists, with more or fewer users and even empty lists. So if doing this optimization for the data acquisition part made sense, wouldn't it make sense to do the same for the business logic part? In this example, I understand that the entire functionality is calculating an average, but what if it wasn't? Besides, even if it were so, calculating an average can be quite difficult. Who said it has to be a simple mean and not some sort of nasty weighted geometric mean? In the end, it doesn't even matter what happens in the calculator dependency. All that matters is that our method returns the exact result from the dependency and nothing else. So if I was to write a test, it would ideally test that the method returns the same value as the dependency, and it wouldn't be concerned with its actual value. It could be 0 or 1 or positive infinity. Let's try and do this now. So again, all I have to do is go into the math calculator and extract an interface for it as well. So extract interface, let's call it iCalculator. Next. And all I have to do is go in this constructor and use base type. And again, if everything went well, our test should still pass. And it does. All right, so I'd venture to say now we're moving from quantitative unit testing to qualitative unit testing. And you'll see in a second what I mean by that. I'm going to write a new kind of test. Like I said, we're moving from a quantitative kind of testing to a qualitative kind of testing. And allow me to paste some code in here and I'll walk you through it. Let me just import the right dependencies and I'm just gonna format this a bit. All right, let's unpack this. So what we have over here is the setup of our system under test, and we're injecting mocked objects based on these contracts. Okay. Then we are exercising the system under test, basically invoking our method and capturing the output in this variable. And then in the assert section, we make sure the returned average value is the expected value, and we'll see in a second where this is coming from. And we're checking that the dependencies have been exercised, have been called with the right arguments in the right order and for the correct number of times. Let's have a look at the math calculator mock setup. And what's happening here is that we're instructing our mock that whenever its method is invoked with this particular list of integers, list of numbers, it should return this particular value. And this is exactly the value we're expecting to see as an output of our system under test, of our method. So what we're trying to ensure here is that the system under test, our method, always returns the exact same value that this dependency gives it in turn. So whatever the value returned by the average calculator, the math calculator average method is returned, this is exactly the same value we get as an output for this method, but only with the condition that this average receives as an input this precise sequence of numbers, this precise list of integers. As for the other mock dependency, if we take a look, again, we're instructing this mock that represents the user reader that whenever this method is invoked, obviously without any arguments, it should return us this precise list of users. As you can see here, this list of users is generated randomly at each run of this test, just to emphasize the fact that we don't care about the actual users in the list. It could be an empty list, it could be a list with one user, with 100 users, doesn't matter. We don't care about the actual values. And it's the same over here for the first mock. We're generating a random list of numbers. Again, just to emphasize the fact that we don't care about the actual numbers in the list. We care about that if invoked with this particular sequence of numbers, then we return this particular, again, random average. All we care about is that these values are threaded through our method in the correct way. We don't care about the actual values. Let's try and run the tests now and see what happens. See if you expect the output. Let's see. Do you expect the test to pass or to fail? Indeed, it fails. Now, why is that? Now, this is due to the fact that although we instructed each mock to give us the correct output back and to react to the correct type of input, namely for this one, a list of integers, these two pieces of information are not correlated the same way they are correlated in the system under test. Let me explain. In the test, the random list of users and the random list of user ages, the random list of numbers basically, are generated independently. So yes, they are random and they are different from each other. They have no correlation. Whereas in the system under test, the list of numbers given to the average method is a projection of the age property of the list of users given by the first mock. So this is where the discrepancy comes in, that the test is expected to work in a certain way, a way which is different from how the system under test works. So obviously, because this list and this list have nothing to do with each other, there is no correlation between them, and the mock calculator has been instructed to only return this number whenever called with this particular sequence of numbers. Obviously, this doesn't happen in the system under test. Obviously, this average method is invoked with a different list of numbers which represents the ages of these particular users. Since this list of numbers has been generated totally randomly and has nothing to do with the ages of the original users, obviously, from the point of view of the mock, this method has never been called because it's never been called with the expected argument. So what we have to do to make the test pass is to replicate the same correlation in the test as we find in the system under test. So what we have to do is basically replicate the functionality that we find in the system under test, replicate it in the test itself. So now if we run the tests, this test should now pass. And it does. But this is wrong. And it's wrong because in order to test some outward behavior, outside behavior, namely the orchestration of these dependencies, hence the name of the test, what we had to know is we had to have inside knowledge about implementation details that should be known only to this method, but we had to have this knowledge in order to make the test pass. But this is wrong, and I'm going to explain to you why this is wrong. Well, what we had to do in order to make the test pass is to have inside knowledge of what's happening between calling the first dependency and calling the second dependency. So we had to have knowledge that between acquiring a list of users and passing in a list of numbers to the math calculator dependency, some sort of mapping happened. And this is wrong because this is what's called a leaky abstraction. In order to use it, I have to understand how it works. The tests themselves, being clients in turn, they have to have this inside knowledge about how stuff works, and that's wrong. That's how you get brittle tests. So the root cause of the problem is that the contract we defined for the math calculator dependency is wrong. It's wrong in the sense that it does not serve its client. So although it exposes the right behavior, like calculating the average, it does not do so with the correct data structures. So it's not speaking the same language as its client. The client's language is, I have a list of users for which I want an average to be calculated. Whereas the contract says, I only care about the list of numbers. If you give me a list of numbers, I'm going to give you the average back of those numbers. So what's happening is there's a mismatch between the language the client would like the contract be expressed in and the actual language the contract expresses itself. So all we have to do is change the contract so that it speaks the client's language. It's simple to do this by changing the signature of our method inside the contract. So all we got to do is change the input type. Instead of a list of numbers, now we get a list of user models. Obviously, we have to change the implementation so that the implementation knows what property on the user object calculate the average of. Obviously, we have to change our system under test because now its dependency speaks the same language as it does, so no need for hidden shenanigans. And obviously, we have to change the test. Now, we don't need to care about a list of numbers, whatever those numbers represent. And our mocks can talk to each other speaking the same language. So the math calculator mock can now accept a list of users, and we instructed that if it receives a list of users, it should give us a random value back. And obviously, when we verify that the mock has been called, we have to check that it's been invoked with the proper list of users, which is the same that the user reader mock returns. So now if we run the tests, this orchestration test should pass. And it does. Now, what's happening is our test now passes, but it's no longer concerned with implementation details. All it cares about is that the dependencies given to the system under test, to our method, are used in the correct, proper way. So you call first the first dependency, the user reader. The output from this one, you give it back to the second dependency, the math calculator, and whatever value this guy gives you back, you give that back to your calling code. That's all you need to do and all you need to know. And just as a bonus, we can, we can inline this variable and even turn this into an expression body, into a lambda expression. And what we have here is basically function composition. So I'm invoking first the first dependency. The output of this one, I'm passing in as an input to the second dependency. And the output of this one, I'm just returning as is, no changes made to it. And this is the single responsibility of our system under test, to orchestrate dependencies. And that's it. Finally, our method adheres to the single responsibility principle. The tests have evolved from being quantitative, caring about this or that user or whether the average is this much or that little, to being qualitative, caring about how dependencies are called and when. This is called orchestration, and orchestration is a responsibility in itself. Orchestration is now the single responsibility of our method. Of course, more tests are needed for the dependencies themselves, but that's another topic for another time. You might argue that the tests are now tightly coupled to the implementation details, but that's not quite true. The method's actual responsibility is to ensure that those dependencies are called in the exact same way and the exact same order. And that is all that the tests are testing. Sure, if tomorrow the way the dependencies are called changes, our tests should change as well. But that is the only reason for the change. And I would really like to hear your opinion about this, so feel free to comment down below. If you found any of this remotely interesting, please consider leaving a like and even subscribe. Thank you everyone, and see you next Codesday.